Let's look at maxima and minima type problems, and they're basically word problems which we want to convert into maths so we can solve it efficiently. The sort of ones we're going to look at, yeah, you probably can reduce them down to two equations. There might be more, but usually there's going to be two. And it's very easy to work out what those equations are going to be, because in the question they'll say, find the maximum of this or find the minimum of this. Well, that means we need an equation for whatever it is we're maximising or minimising, and we then need some given information to link into that. So some piece of information they'll give me and I can create an equation from that. Once we've done that, then I'll rewrite the one I'm trying to maximise and minimise so it's in terms of just one variable, and then when it's in terms of one variable, I can then go and use calculus to go and solve the problem. Here's an everyday problem. I'm sure you've had one like it yourself. We have a rope 36 metres long in length, and we're going to cut it into two pieces because what we want to do is create a square and a rectangle. Possibly we're going to put them on the ground so we can get our bug and capture it inside some sort of cage. That might be our problem we're trying to solve here. But our rectangle has to have one of its sides the same length as the square itself. But we're trying to maximise the area for this bug to travel in because we want it to have a good life. We don't want to just, like, you know, for instance, throw it out the door or something. Okay. Pictures are great because I can visualise the problem. I've got a square, I've got a rectangle. My rectangle has one side the same length as the square. Let's give it some dimensions. Well, side of a square, let's call it S. The rectangle, S, well, the other side I'll just call R for rectangle. We're trying to maximise, where it is, the area. I need a formula for the area of these two shapes then, S squared plus RS. Now for the information that will link into that. We've been given the length of the rope, which when you think about it becomes the perimeter of these two shapes. I know that 6S plus 2R is 36. Beautiful. I'm going to make R by the way, I probably wouldn't write down make R the subject. This is just me explaining it, of course. I'm going to make R the subject in the second one, substitute it into the first one. Now I could have made S the subject if I wanted to, but why make life hard for myself? If I'm substituting into the area formula, it's probably going to be easier to substitute into R. I've only got to substitute into one spot than substitute into two spots. It doesn't actually matter, but I'm going to go with that. So R is 18 minus 3S, substitute it back in, and I get a nice formula which I can tidy up. There it is. Now it's at this point I've actually got a couple of ways I can now solve the problem. Probably the most efficient way is not the way that I'm about to do. The most efficient way is I'd look at that and say, hang on, that's a quadratic. And if I'm trying to maximise my quadratic, it's an upside down parabola, I know that's going to be at the vertex. I'll just find the axis of symmetry. That would probably be the most efficient way. But of course that would then make it a stupid example of using calculus to solve it, so let's use calculus. There's my function, differentiate it. I'll differentiate a second time as well because I need to work out is it a maximum or is it a minimum. I know my stationary points will occur, and in this case my derivative is dA ds. When that is equal to 0, solve that. 9 on 2. I know that when 9 on 2, the second derivative is negative 4. It's actually negative 4 everywhere. But that's less than 0. So yes, I know when the side of the square is, and rather than say 9 on 2, because it's a practical problem, it probably makes more sense to say 4.5 metres. Because if someone was to say to you, how long is this? You're not going to go, oh, it's 9 over 2 metres long. No, you'd say 4.5. 4.5 metres, the area is a maximum. Notice I did not bother finding the area. They didn't ask me that. Why do work that I don't have to do? It simply said, find the side length of the square. Interestingly though, what does that mean about our rectangle? Yeah, it's a square as well, because we had a formula. Where was it? Let's go back to it. We worked out here that the side length of the rectangle was 18 minus 3s. You substitute that in, you'll also get 4.5. And that happens an awful lot in optimisation problems, where the maximum areas, things like that, happens with the what you would call the perfect shape. And I guess the perfect rectangle is when all the sides are the same. So it would have the maximum. So we see that a lot. Okay, let's do this one. We have an open cylindrical bucket, and we're going to hold the largest possible volume in the liquid, because ideally, we've got a bucket, we want to get as much into it as we like. We know the total surface area of the material we're using, conveniently, is a multiple of pi. Oh, that's nice. 12 pi. Also, for this practical problem, we're going to be actually able to use every piece of material that we're going to use. Of course, in the real world, there'd be wastage. You couldn't actually get it perfectly. And in the real world, you'd have another equation for wastage, and you'd want to minimize the wastage, maximize that, and you have a whole combination of it. But this is a very simplified problem. Alright, there's my bucket, which happens to be a perfect cylinder. Again, in reality, buckets probably are tapered and what have you. We're trying to maximize the volume. We know that's pi r squared h. The material we're using will be exactly the surface area of our bucket, and it's 12 pi. All I have to do is remember this formula for the surface area of a cylinder, which is, of course, close. Yes, we have an open bucket. If we were going to use the actual surface area formula for a cylinder, we'd have a problem with our bucket, because we don't want a circle on the top. Otherwise, the liquid's not going to get into the bucket. So for this one, it's just going to be pi r squared plus 2 pi r h. Okay, now I want to create an equation for volume so it has one variable. I'm either going to make h or r the subject. Well, there's a couple of reasons why I'm going to choose h here. It's going to be easier to substitute in, but also, gosh, it's going to be a lot easier to make h the subject of this than make r the subject of that. So let's make h the subject. There it is. Substitute back in. Oh, let's tidy that up. We get a cubic. It's not our perfect cubic, which has that one horizontal point of inflection. It'll be one of our, for want of a better word, twisty cubics. So we'll have a maximum point and we'll have a minimum point. Right. Let's find the tools. First derivative, second derivative, stationary points. In this case, it's dvd r equals 0. We end up with two possibilities, plus or minus 2. But remember, we're solving a practical problem here, so the choice of the one I'm going to test becomes a little bit obvious. It's going to be plus 2. So I don't know about you, it's going to be really hard to make a bucket with a radius of -2. It makes more sense that it would be 2. But with r equals 2, I get minus 6 pi, which indeed is negative. Thus, when the radius is 2, the volume is a maximum. What would happen if that turned out to be a minimum and actually -2 was the maximum? What would this mean for our problem? Would we say, oh, the maximum is going to occur when the radius is -2, which of course is ridiculous? Again, think about the picture. We would end up with a graph. I'm saying the maximum's at -2 rather than +2. Okay. Theoretically, what's going to happen here is, well, we've got a minimum at 2. We want maximum volume. Therefore, in our domain, well, it might be at 0. Well, infinity? It's not going to be an infinity, but it's going to be at the extremes of the domain, I guess, for that one. There would be a logical end to the domain, I guess, because of the amount of material we're using. There'd be a maximum that the radius could be. It makes it a far more challenging problem, of course, so lucky for us, it turned out to be a maximum, and we don't have to worry about that. But answer the question that they've asked me. They asked me to find all these different things. The height turns out to be 2 as well. What a weird bucket. The height is 2, the radius is 2, so we've got a really wide bucket, but okay, it's a bucket. And the volume ends up being 8 pi. There we go. Okay, so for H and I are playing with our maximization, minimization, or if we want to use just one word, optimization problems.